So this is Griffiths Electrodynamics problem 4.18. We're going to be looking at a parallel plate capacitor, and for the sake of this problem, we're going to treat these planes as infinite, right? So yeah, uniform fields, all that stuff. And yeah, we've got two pieces of dielectric in here. They're each width of A, two different dielectric constants. In fact, I believe I'm going to try and use different colors, right? I believe the dielectric constant of this first one is 2, and the dielectric constant of this other one is 1/2. Or sorry, 1.5, or in other words, 3/2. Let's go ahead and put tiny little subscripts on these guys. Plus the colors, I hope, will help us keep them straight. So we're just going to go through a series of questions about this capacitor, starting with the electric displacement. So for this, we're just going to use Gauss's law. So electric displacement and Gauss's law. So we'll be using the displacement version of that, right, where we only look at the free charges, and we'll just picture a little Gaussian pillbox of surface area of each side of A, big A, let's say. And so if we take, say, the top surface here, and we have a little Gaussian pillbox that we are putting, sandwiching this surface with, right? Gauss's law gives us this. This is a free charge enclosed. Okay, so the for Gaussian pillbox, right, as we squeeze it down tight, the surface area is just A for the top and A for the bottom. So we just get a 2A here. This is all just very similar to what we normally do for to find the electric field of an infinite sheet of charge. We're just kind of going over it again. The free charge here is just the surface charge density multiplied by the surface area enclosed in this Gaussian pillbox, which is just A. Okay, therefore D is equal to sigma divided by 2. Okay, and just like so if we're looking at just one sheet of charge, right, by symmetry we get the same amount in each direction. So say we're looking at just the top sheet of charge right here. I'm going to draw D here. I'm just going to write this sigma over 2 coming in, going in each direction. And this is uniform, right, because the sheet of charge is infinite. All right, but in our case, of course, we have two sheets of free charge, right? There are other charges in this problem, bound charges, especially like at this interface here. But for free charges, the free charge for this form of Gauss's law, we only have these two surfaces where that's an issue. So if this one is sigma and this one is minus sigma, well, we just carry this minus sign through the same thing. And for the bottom, we'll just get a minus sign right here, which tells us that for this one, D is pointing towards. So the minus sign just changes the direction is kind of what I'm doing. So it's still a sigma over 2, except now it's pointed towards the sheet of negative free charge density. All right, and this also for this sheet, it also affects on the other side of the top sheet. All right, and the displacement from this top sheet is also in effect here on the beneath the bottom sheet. Right, it's just uniform, goes on forever. But the the thing of it is if we look at just the top, these two will cancel out because they're in opposite directions, and these two will cancel out because they're in opposite directions. So our answer for this portion of the problem is that we're just looking for the displacement between these two sheets of charge, right? That is in this red region and also this green region. And it's the same in both because they're both, it's all due to just the free charges, right, on the very top and the very bottom. And we just add these together. So D is equal to sigma over 2 plus sigma over 2, which is just sigma. So here's our magnitude, and maybe we should, let's go ahead and define a direction for this. What shall we do? Let's just call up Z. So I'm going to just draw a Z hat vector pointed up. So in that case, if we want to make this a vector, it's actually in the minus Z hat direction. And that's our answer for part A. The magnitude of the displacement is just sigma, and the direction is, of course, pointed away from the positive free charge surface density and pointed toward the negative free charge surface density. So there we go for part A. Now for part B, we're going to find the electric field in each of these two slabs, this orange one and this green one. Excuse me. So we'll set this aside, and to find the electric field, let's see. These are linear dielectrics, right? So we know our displacement, which is defined as epsilon naught multiplied by the electric field plus the polarization. Because these are linear dielectrics, we can write the polarization as the permittivity of free space plus the electric susceptibility of whichever dielectric we're looking at, and it's proportional to the electric field. Linear dielectric. Okay. So we've been through this before, but if this is the first problem you're looking at or whatever, then it's good to go through this. So here we go. This term in parentheses is called the permittivity, or excuse me, the dielectric constant. All right, so epsilon naught, the permittivity of free space, multiplied by this, which is the relative permittivity or something like that, or in other words, the dielectric constant, epsilon sub r, and then of course our electric field comes down. Epsilon naught times epsilon r is equal to just epsilon, also known as the permittivity. So again, this is just for linear dielectrics. We go over this every single time, seems like. So yeah, if we know D inside these slabs, right? It is the same for both of them, and it's just sigma, and then a direction pointed down. Now to find E, we just divide by epsilon. So let's look at this original one right up here. All right, E, and we'll put a little subscript 1 on it, right, is equal to this displacement divided by the permittivity, just this right here, except we'll call that permittivity 1. There's a gajillion different subscripts for these epsilons, so it's kind of hard to keep them all straight, but we'll try and do that. Okay, again, our displacement was just sigma in the minus z hat direction, meaning pointed down. What is epsilon 1, right? That's just the permittivity of the red slab right here, which in turn is equal to the permittivity of free space multiplied by the dielectric constant. And the dielectric constant, just making sure I wrote these down right, for the red slab, that is equal to 2. So here we go. Here we have, maybe not the cleanest way of writing this, we could bring out this minus sign and stuff. But there is the electric field for the red slab. So moving on to the green slab, we'll call that E sub 2, okay, is the electric displacement divided by epsilon 2, meaning the the permittivity of the green slab, which we can again plug in our sigma in the minus z hat direction. And then we have our permittivity of free space, epsilon naught, multiplied by our dielectric constant, 3/2, which down here we can write the 3 downstairs and the 2 upstairs. So here we go. Here's our electric field in the top half. Here's our electric field in the bottom half. Now we are going to move on to the polarization. Let's see how we can do this. So now we know the electric field and the displacement field. So let's again just write out this little definition of D. Okay, so now we're solving for P. And that is just equal to D minus epsilon naught multiplied by E. So we know what D is for each of these slabs, and now we know what E is. We just found that over here. So let's look at the red one first, which we of course will call P sub 1. D, of course, is again just sigma in the minus z hat direction. Okay, and then we're going to minus epsilon naught multiplied by E sub 1. Again, we're just focusing here on the top slab, which is this right here. So we have a sigma, we have again our minus z hat, and then on the bottom here we'll have this 2 and this epsilon naught. And of course these can cancel out. So let's go ahead and write this a little bit more cleanly. So we have, what do we have here? I'm going to go ahead and write, I'm going to keep this minus z hat separate. I'm going to keep the minus sign with the z hat. Just, I think it helps us visualize the direction of the field when we do that. So here's our sigma. And then we have a 1 minus 1 over 2. Right, that's what's left here. And of course, we're keeping our minus z hat still here. So 1 minus 1/2 is just 1/2. We just get a sigma over 2 in the minus z hat direction. Okay. Just trying to find in my notes, make sure I'm doing this right. Yeah, I think so. Yeah. Looks good, I think. All right, let's look at polarization for the green slab now. Okay, this part down here. Here's our electric field piece. So again, we're just looking at this equation that where we solved for the polarization. Our displacement is the same as before, right? Still just a sigma in the minus z hat direction. And now we have a minus epsilon naught multiplied by this electric field now, which is a 2 sigma in the minus z hat direction over this epsilon naught and 3. These will divide out, of course. So basically we have 1 sigma minus 2/3 sigma. So just a 1/3 sigma left. So sigma over 3. And this is still in the minus z hat direction. Let's just make sure that works really quick. This whole minus, notice they're both in the minus z hat direction. What does that mean? Well, it just means that if we look at the bound charges, we get a bunch of minus bound charges right up here, which makes sense, right? Because the minus bound charges they get pulled towards this positively charged plate. And a bunch of little positive bound charges in the red section here, right at this interface. All right, so minus up here, positive down here, our polarization points towards the positive, pointing down, minus z hat direction. For the green, we get a bunch of minus bound charges here, which are attracted to the positive bound charges in the red. Okay, and then positive bound charges here, which are attracted to this minus sigma, the free charge surface density here. So anyway, again, we have polarization pointing in the minus z hat direction. So we have found the electric displacement, we found the electric fields, and now we've found the polarization in these two different slabs. So we are now going to find the potential difference between the plates. That's fairly easy, right? Once we know the electric fields, we can just add them up. Meaning, what we're doing is that integral where you integrate. Let me write it out real quick. Right, we have the minus sign. We're going from some origin up to some reference point, and it's the electric field dotted into your displacement vector. All right, this is what we're doing, but because our electric field is uniform, we can just multiply it by the distance rather than doing doing out the integral, right? E is just a constant in each region. Pull it out, and then the integral of this dl just gives us this distance. So v, we're looking at potential difference, right? So this is just like a delta v. All right. Switch to red. This will be E1 multiplied by A. This A is the distance or the thickness of the top slab where the electric field is given by E1 plus E2 multiplied by A. So now we just go back and we find our electric fields right here. Okay, we just multiply by A. Couldn't be much easier than that. In fact, I'm just going to bring the A out because it's the same. Maybe I shouldn't worry so much about colors right now. I'll just do it in blue. So I'm going to factor out the A. So that's this A and this A. Looking at our two electric fields, E1 and E2, we see there's a sigma for both of those. There's also this epsilon naught. There's also, of course, the minus z hat direction vector, right? What's left over? We have a 1/2 right here, and we have a 2/3 right here. So let's put those in, and this time I will use color. So we have a 1/2 plus 2/3. All right, what do we get now? So finding a common denominator for this, this is a 3/6 plus a 4/6. So 7/6. 7 over 6 A sigma over epsilon naught. And maybe we shouldn't have a vector in here, right? Yeah, we shouldn't, because this is a dot product. The vectors, anyway, the potential is a scalar, right? So this is just 1, right? Maybe we can keep this, well, anyway, let's just talk about the magnitude of this. All right, which one's at the higher potential? Well, the top plate, because that's where the positive charge is. All right, the bottom plate's a negative charge. That's at a lower potential. A test charge will move from the top to, or want to move from the top to the bottom. Okay, so great. Here we go. Just double check. Yep. Same. Okay, we're good on. We're on the right track. Okay. Now we're going to find the location and amount of all the bound charge. Now, so there's two kinds of bound charge that we would encounter. One is a volume bound charge density, which is the divergence of the polarization, right? All these fields are uniform. The polarizations are all uniform. So the divergence is equal to 0. So we're not dealing with a volume bound charge density here. We're dealing with a surface bound charge density. in a few different locations. One at the top surface of the red, one at the bottom surface of the red slab, top surface of the green slab, and bottom surface of the green slab. And the amount of bound charge is going to, of course, depend on these two different dielectric constants. So, if we look up the formula for a bound charge, surface bound charge density, right, we get polarization dotted into a normal unit vector. What's the normal unit vector? Well, that just depends on the surface that you're looking at, right? Which way is it facing? You know, surface facing this way, surface facing that way. Personally, I'm just going to keep track of the sign of the bound charge just based on the physical reason, right? The negative bound charge for the top surface of the red, the bound charge density for the top surface of the red will be negative because it's right up next to the positive free charge surface density. All right. So for bound charge, it just goes negative and then positive and then negative and then positive down here. So rather than worry about like which way the little vectors are pointing and stuff, we'll just use that. So that's just the polarization, which we found right here. So let's draw this out just so we try to keep things as clear as possible. I'm going to draw this nice and big because I'm hoping to use this picture later on for the last part of this problem where we use all of the charges, bound and free, to try to recover, anyway, we recover our original, from part B, the electric fields that we found for the two parts. So I'm going to use colors here, and I hope this helps us keep track of all this stuff. Let's write in our free charge surface densities really quick. There's a sigma up here and a minus sigma down here. All right. Now again, what this equation tells us is that the bound surface charge density will just be the polarization, and then this dot thing is just to help us keep track of the sign and stuff. I mean, I guess it might, if our interfaces were at some weird angle, then it would become more complicated. But since everything's flat, this dot product just gives us a +1 or a -1. We're just going to keep track of the charge based on what it's close to. So looking at the magnitude of P1, we just get a sigma over 2. So that tells us that the magnitude of the bound charge density for the red slab is sigma over 2. And one of them is going to be negative. We know which one because we know that the top free surface charge density is positive. So the one that's next to that will be negative. These negative bound charges are attracted to this positive one. Looking at the green one, we look at the magnitude of our polarization and we get a sigma over 3. So the magnitude of these are sigma over 3. Which one is positive now? The bottom one is positive. Again, well, I guess the bottom one was positive on this one too, right? The positive bound surface charge is attracted to this negative free charge down here. So this one's positive, this one's negative. And of course, this negative is attracted to this positive, you know. So anyway, it just goes positive, negative, positive, negative, positive, negative. So, so we've now done part E. Find the location and amount of all bound charge. Now that we know all of these charges, we're going to go back and calculate the electric field in these two regions, just using Gauss's law again. Okay, so I hope I can do this without being too confusing. Gotta do something about my cough. Let me write the total charge at each of these interfaces. Okay, so here we have a sigma of plus charge and a minus sigma half of minus charge, right? So the total net charge, whether it's free charge or bound charge, is just sigma over 2, surface charge density. All right, for this case, what would this be? This would be 3/6 minus 2/6, so just 1/6, and that's positive, sigma over 6. And then down here, we have a minus sigma plus a sigma over 3. So that's a minus sigma, minus 2/3 sigma. Okay, and does this all make sense? For one thing, all of these should add up to 0. So this would be 1/6 plus 3/6, so 4/6 positive, which is 2/3 sigma positive, and a minus 2/3 sigma, right? So the whole thing's neutral. That's good. Yeah, so I think, anyway. All right, so let's look at these using Gauss's law, and we're going to use, what are we going to do? We're going to use the electric field version of Gauss's law now. All right, because we're dealing with all charges, not just free charges. So we have E dot dA equals the total enclosed charge over epsilon naught. Let's look at these 3 regions. So kind of what I'm going to do here is try to follow, you know, what we did at the very beginning, where we just had our 2 parts. We used the D version of Gauss's law, and then we just summed up all the pieces, you know, outside on both sides, and then, you know, those 2 parts canceled out. I have it. Where do I have it? Here it is. This is what I'm gonna do, right? We just canceled those out. Yeah. So just so we know where we're going. All right. So looking at first at this piece. So of course, say we take a little Gaussian pillbox here, right, and we squeeze it down right at the interface. The surface integral will then just be the area of the 2 faces. All right, so that's a 2A if the top and bottom each have a surface area of A. 2A, and then we have an E. The charge enclosed is, well, it's this sigma over half now, right? That's the combined charge density of the free charge and the bound charge. So sigma over 2. To get charge from charge density, we have to multiply by an A. And of course we have epsilon naught down here underneath. So this gives us an E is equal to, all right, the A's are going to divide out. We have a sigma over 4 epsilon naught. All right, that came from this piece right here. All right, on to the second piece. The only difference between these two is here we had a 2, now we'll have a 6. So let's write that out real quick. Or in other words, we get E equal to sigma over 12 epsilon naught. All right. And finally down here at the bottom, now we have this minus 2 over 3 part. Okay, which gives us an E equal to, the 2 is going to divide out. We have our minus sigma over 3 epsilon naught. All right, so now we have our 3 pieces, and it's not very clear right now what this means. So what I want to do now is just write these in here like we did previously for our previously when we found the displacement. So let's start here at the top. E equals sigma over 4 epsilon naught. Notice these all have a sigma over epsilon naught, so maybe we can not write that part. Okay, they'll all be multiplied by sigma over epsilon naught. We'll just add it in at the end. All right, so we have 1/4, all right? And it's positive, so it's going outward. So I'm writing 1/4 here. And I'm going to just, so say from this region here, it's going 1/4 that way and 1/4 this way. It's outward. All right, and this continues through all of the regions. Now we move on to this one. We have a 1/12, and it's positive, so it's going outward from this region now. So outward from that region and outward. And of course it continues all the way to the outside, both up and down. And then finally we have a minus 1/3. And that's due to this region right here. So since it's minus, they'll be pointing towards this bottom layer. And it's a 1/3. Pointing towards the bottom. Kind of a weird problem, huh? Okay, so now we just have to add up these different pieces, and then we'll look at comparing them to what we've found before. All right, but we have to notice the direction the arrows are going. So let's just say up is positive and down is minus, right? All right, so looks like 1/12 is going to be the common denominator for this. So we have a 3 and a 9, or sorry, a 6. So 3 plus 6 is 9. And then a minus 4. Let me just double check this, because what we want to get is 0, right? So maybe I messed up something. 3, 6. All right, let me see if I can find a mistake. Yep, I wrote 1/2 here. That's a 12. See how these are all 1/12, 1/12, 1/12. Okay. This is a 1/12. All right. So, sorry. So we have a 1/3, or sorry, a 3/12 going up, plus 1/12. So that's a 4/12, and then 1/3 is also 4/12, except it's going down. Therefore, cancels out. All right. If this, yeah, feel free to. I hope this is clear enough. Pause the video if it's not good enough. Think it through. 1/4 is equal to 3/12, and then add on 1/12. That's 4/12. 1/3 is also 4/12. Same thing happens. We get a 0. Right. So far those have checked out. We do get electric fields of 0 on the outside of our capacitor. And note that we do still have to put in a sigma over epsilon naught once we find the coefficient that goes in front of it. Maybe I can write this right out here. So what do we have now? We have 2 of them going down and then 1 going up. So 1/4, there's a 3/12 and a 4/12. That's 7/12 minus, right? So going down, and then a 1/12 going up. So that's a 6/12 or 1/2. So we just have a 1/2. Oh man, it's drying out a little bit. Okay, so we have a 1/2, but it's going down. So I'm gonna write that like we wrote before, minus z hat direction, and then to make this an electric field, we had to add in our sigma over epsilon naught. Okay. This one, they're all going down. So the 1/4 and the 1/3 again, what does that give us? That gives us 7/12. One more gives us 8/12, which is what? 2/3. Okay. So we have a 2/3. We'll have our sigma over epsilon naught, and they're all going down. Our electric field is pointing downward, so minus z hat direction. So now we found our electric field from the total charge, bound and free. The amount and the location, all that stuff. We found our electric field. Let's go back and compare to what we found before. All right, here they are, E1, E2. Right, we already knew that the electric field was 0 out here because the whole thing's neutral, right? And well, yeah, well, because of the symmetry and stuff too, so that's important. It was, yeah, so 2 sigma over 3 epsilon naught, 2 sigma over 3 epsilon naught, minus z hat direction, and here we have sigma over epsilon naught, and our 2, again in the minus z hat direction. So yeah, it checks out. We got back our same electric fields the way we found the previous way, but just note how much easier it was the first time, right? We didn't have to do all this summing up of all the different charges and all the long version of Gauss's law. You know, once we found the electric displacement, we found the what did we do? Yeah, just straight from that. Once we found the electric displacement, we just divide by these permittivities, right? Anyway, it was a lot faster the first time. So yeah, that concludes this problem. It's kind of it's not too hard, but it just kind of dragged out for quite a while.